Okay, in this supplemental video on method of substitution, I'm going to walk you through several additional examples of substitution just for the practice. I have the integral of 1 over x natural log of x quantity cubed. So looking at this question in the beginning, it may not be completely clear that method of substitution is what we need to use here, because where is the product, right? But let me rewrite this expression just a little bit so that the product becomes more clear. I'm going to rewrite this as the quantity 1 over x times the quantity natural log of x to the power minus 3. Recalling that negative exponents are equivalent to pushing the quantity into the denominator of a fraction. So now I can more easily see the product, and not only that, I can see the product of a function, expression involving a function, in this case natural log of x, with the derivative of that function. 1 over x is the derivative of natural log of x. So having recognized that this is probably a situation where method of substitution would be useful, I'm now going to proceed with that method. I'm going to go ahead and set u equal to the function natural log of x, whose derivative is this 1 over x sitting out in front of the product. And I'm going to use that function and its derivative to give me information to replace this natural log of x, with something containing u, and to replace this dx with something containing u instead. Now, if I stick that information into the expression, that natural log of x to the power minus 3 now becomes u to the power minus 3, and the dx in the back now becomes x times du. And as a result of choosing my u wisely, I now have the ability to cancel out this 1 over x and this regular multiplied x, leaving me with an integral containing u only. And a very, very simple, nice integral as well. This is an integral that I can calculate using just power rule. Now that I've calculated the antiderivative / indefinite integral in terms of u, the only thing left for me to do is to put back the original variable x. So my final answer to this question would be natural log of x in place of u to the power minus 2 all over minus 2 plus c. This expression here, this function, would be the indefinite integral of this original function. Okay, example number 2. I am asked to calculate the integral of x squared times the square root of 1 plus 16x cubed. So once again, I'm drawn toward method of substitution because I have a product, x squared times this other expression. And additionally, I have a product where I have some function, namely this entire quantity under the root, as well as something that is very closely related to the derivative of what is under this root here. So let me try to set u equal to this big complicated expression under the root. If I set u equal to this big complicated expression, then du would be equal to 3 times 16 would be 48 x squared dx. And so dx would be 1 over 48 x squared du, just by dividing out to isolate dx. Now let's put that information into this expression and see if what we get at the end is a nice simple integral with only u's and no x's. The x squared in the front stays put for now. The square root of this big complicated quantity is now just the square root of u. And the dx in the back is now 1 over 48 x squared du. Behold, I have now achieved a cancellation of this x squared in the front and this x squared in this denominator. So what is left is a really simple integral, 1 over 48 u to the power 1/2 with respect to u. And this is an integral that I can calculate just using power rule. Copy paste the constant multiple, increase the power by 1 unit, and divide by the increased power. Then all that's left for me to do is go into this expression and put back, instead of u, put back the expression in terms of the original variable x. So putting back in u's place, this expression 1 plus 16x cubed, I get this indefinite integral 1 plus 16x cubed to the power 3/2 plus c. This expression, and you can simplify it if you want to, this would be the indefinite integral of this function. Now notice that as I am trying to do my substitution and as I'm choosing what u should equal, I generally try to make u complicated. I tried to make u contain all of this complexity that is underneath the square root. So I make u equal to the entire quantity 1 plus 16x cubed because if I make u equal to this entire quantity, then when I do the substitution, what ends up underneath the square root is really, really simple and really, really nice. My goal doing this substitution is to make the integral in terms of u as simple as possible. And so to that end, I tend to make u contain as much material as possible so that when I do the substitution, what is left is as simple as possible. Okay, so another example. Here I am asked to calculate the integral of x divided by 1 plus x squared. So first of all, where is the product? Where is the sign that method of substitution would be useful in this case? To see the product, I'm going to go ahead and rewrite this fraction slightly. Not x divided by 1 plus x squared, but x times 1 plus x squared to the power minus 1. So now I can see the product, and also I can see that I have a copy of a function, in our case the function 1 plus x squared, and as well the product is containing something very closely related to the derivative of that function. So if I let u equal 1 plus x squared, a nice complicated u, then du would be equivalent to the derivative of this, 2x, times dx. So dx would be equivalent to 1 over 2x du. And let's see what happens to this integral if I put this information inside. I have the integral of x times what is now u to the power minus 1. And that dx is becoming 1 over 2x du. And as a result of how I've set things up, this multiplied x in the front and this divided x cancel. And so I'm left with this integral, nice simple integral, in terms of u alone. And I can integrate this just using the formula for the integral that involves the natural log, 1/2 natural log of u plus c. In this situation, the only thing left to do to finish this up is to put back the original variable in u's place. So I get 1/2 natural log absolute value of 1 plus x squared plus c. This would be the indefinite integral of this expression. One more. Here I am asked to calculate the integral of e to the 3x dx. Now at first glance, this may not seem like a particularly good example for method of substitution. because where is the product, right? But in this particular case, I think there is a kind of hidden product between e to the 3x, and you could think about it as just a constant, like a constant function 1. In this case, I have a sort of hidden product here of the function and 1 unit, and I also have a copy of a function, in this case 3x, with something very closely related to the derivative of 3x, namely the number 1. If I set u equal to that 3x in the place that is normally occupied just by x in the exponential, then du would be equal to 3 dx, and that gives me 1/3 du is equal to dx. If I make that substitution, then the integral of 3x dx becomes the integral of e to the u 1/3 du. Integral of e to the u times 1/3 du. Now, what was the advantage of making the substitution in this situation? The advantage was, we have a formula for the antiderivative of e to the u du. We have a formula for the antiderivative when there is just a copy of the variable up here in the numerator, up here in the exponent. What we do not have is a formula for the antiderivative of e to the 3x, where there is a 3 up here with our variable in the exponent. So in a situation like this, substitution gives us a way to fix that, to fix the issue caused by having a number up here by the x in the exponent level. If I follow through, finding the antiderivative in terms of u, then I just get 1/3 e to the u, and so the antiderivative plus c is my indefinite integral. And then all I have to do is put x back, so I get 1/3 e to the 3x plus c. 1/3 e to the 3x plus c is our antiderivative of this guy. A problem of a similar nature, here I'm asked to find the indefinite integral of the quantity 1 minus 5x to the power 17. Now, in theory, I could go ahead and multiply 1 minus 5x out 17 times and go ahead and use just power rule and sum rule and difference rule to find the antiderivative. But there is a much, much faster way. And the much, much faster way is to try a substitution where I let u represent this entire quantity inside of the power 17. Let's see if with this substitution, I can get myself a simpler integral that can be expressed in terms of u alone. If I take the derivative of both of sides of this expression, the derivative of u with respect to x would be -5. So if I split those differentials, du would be equal to -5 dx, which means that dx would be equivalent to -1/5 du. If I put all this information into my integral, then I get the integral of u to the power 17 times -1/5 du. And I can integrate that just using power rule, u to the 18 plus c. And all that's left for me to do at this point is go ahead and put that original variable x back into place. -1 5 times 18, whatever that is, quantity 1 minus 5x to the power 18 plus c. Similar nature, someone asked me to calculate the definite integral of 1 divided by 1 plus 2x dx. Now again, it's not apparent that there is a product here, but I am seeing a relatively complicated expression in the denominator of this fraction, more complicated than I actually have a formula to deal with. But if I let u stand in the place of that complicated formula down in the denominator, then du would be equivalent to just 2 copies of dx, which means that 1/2 du is equal to dx. And if I put these three pieces of information into this integral, then I could find an antiderivative of this expression equivalently by doing 1 over u replaces this complicated fraction, and then dx becomes 1/2 du. Now this is really simple, so I can find the antiderivative just using one of the formulas that we have, and then I can put back the original expression in terms of x, where u is. Now that I've found the indefinite integral, and in particular I have found one antiderivative, I can finish this definite integral problem just by plugging in these two x values to the antiderivative and subtracting the results. So plugging in the value of x equals 3 and the value of x equals 1, I get 1/2 natural log of, that looks like 7, minus 1/2 natural log of, that looks like 3. And this value right here, 1/2 natural log of 7 minus 1/2 natural log of 3, would be the exact value of this definite integral.